Okay, this week we're going to talk about sampling distributions and the central limit theorem, which is normal probability distributions continued. So it's the second half to normal probability distributions, which we did last week. So to just recall a little bit from last week, each data value, x, has a corresponding z-score you find using the formula. The z-score tells you exactly how far the data value is above or below the mean. It tells you exactly how many standard deviations you are away above or below the mean. Any normal distribution can be converted to a standard normal distribution using the z-scores. So here you have, this is your any normal distribution that you have. If you convert all your data values to z-score, you get the standard normal distribution, and then you can find your probabilities or areas using our chart. So what we're going to talk about this week is a sampling distribution, which is a probability distribution for the sample statistics. It's based on all possible random samples of the same size from the same population. And the notes, so the notes, if you look at the notes, this starts definitions. This first part here on the slideshow talks about rolling a die. So if you can actually go to the second page first. I was going to move it around, but because of what I've got listed here and stuff, it kind of makes more sense just to leave it here on the notes, but I'm going to talk about this first. So if you'll just skip over to the second page for just a second. So what we're going to do is we're going to talk about if you were going to roll a die, then what is your population for the rolls possible on a single die? So if you're going to roll one die, you can get a 1, a 2, a 3, a 4, a 5, or 6. If you find the mean and the standard deviation of those, it's 3.5 is the mean, standard deviation is 1.71. There's only one possible roll to give you each value, so your distribution would be this. You would have 1, you can get 1 time, 2, you could get 1 time, 3, you get so on. So it's a uniform distribution, it looks like that. Then it says, and this says see notes, list each possible sample, I should say sample mean, and the frequency. List each possible sample mean. I think that's a typo. Let me fix that. Sample mean and the frequency for 2 dice. What sample? Okay. So I have that on the notes typed out, so you didn't actually have to do it. You can do it if you want to, but I have it typed here. There was a typo, so your notes should be fixed. I fixed it over here. So if you're going to roll 2 dice, you're going to have, you can have possibly, this is just listing all possible combinations. So you could have a 1 and a 1, you could have a 1 and a 2, a 1 and a 3, and so on. You could have a 2 and a 1, a 2 and a 2, a 2 and a 3, and so on. So you have, so if you ignore the means for just a second, you have all these possible combinations if you roll 2 dice. Like I said, that should be fixed on your notes now. So what you want to do is find the mean of each of those. So the mean of 1 and 1, 1 plus 1 is 2, divided by 2 is 1. And then 1 plus 2 is 3, divided by 2 is 1.5. 1 plus 3 is 4, divided by 2 is 2. So on and so forth. So you just find the mean of those two numbers, added together, divide by 2. So these give you the means. And then what you do is you make a frequency table based off this. Let me just slide it this way. So here's our frequency table. So for the mean of 1, if you go over here and count, the mean of 1 only occurs 1 time. For a mean of 1.5, it occurs 2 times because it occurs when you get a 1 and a 2 or a 2 and a 1. So mean frequency would be 2. A mean of 2 occurs 3 times. It occurs if you get a 1 and a 3. So there's 1. It occurs if you get a 2 and a 2, and then it occurs if you get a, I lost it. There we go, 3 and a 1, 2. So 2 occurs 3 times, and so on. So you just count how many times does each mean occur. So for us, it goes 1, 2, 3, 4, 5, 6, 5, 4, 3, 2, 1. If you calculate the mean of this frequency distribution, you would find that your mean is still 3.5 and your standard deviation is now 1.21. And the way you do that, type these into L1 just like the old thing, if you can't remember. Type these into L1, type these into L2, go to Stat, Calc, choose one var stats, and then do L1 comma L2, and it'll spit out these two numbers for you. So we've done that before, so I'm not going to go through that again. So if you look here, I have it graphed. This is the graph. A mean of 1 it occurs 1 time, mean of 1.5 occurs 2 times, and mean of 2 occurs 3 times, and so forth. So you can see it is a normal distribution. For n equals 3, how many roll combinations are possible? There's 216, so I didn't have you list those, or I didn't type those out, because that would take a really long time to do. You start with 1, 1, 1, and then you could do 1, 2, 1, 1, 3, 1, 1, 4, 4, 1, and so on. It would take a long time, but there's 216 of them. So you still do the same way. You would list them all like this, find their mean, and then count the frequencies of their mean. So I don't have it on here, but I've already done it here. So the mean of 1 occurs 1 time, mean of 1.3 would occur 3 times, mean of 1.7 occurs 6 times, and so on and so forth. Use the calculator, still find the mean of standard deviation. So type this into L1, type this into L2, go to stat calc, 1 var stats L1 comma L2. The mean is still 3.5. The standard deviation changes to 0.99. So if you notice here on these, our means are not changing. Mean is always 3.5. It doesn't matter. Using our original distribution, it's 3.5. If you roll 2 dice, it's 3.5. 3 dice, it's 3.5. And I think I even have 4. Yes. So the fourth on here, which I don't have on the slideshow, but if you want to roll 4 dice, how many roll combinations are possible? 1,296 would be possible, and you would have to list all those. It would take you a really long time to list that many, but you could if you wanted to, so I've already done it. I think I cheated and found it online somewhere, to be honest, but you get same thing, take the mean of each possible roll. So you'd start with 1, 1, 1, 1 4 times, and the mean would be 1, the frequency would be 1 time. 1.25 would occur 4 times, 1.5 would occur 10 times, and so forth. And just as a reminder, to get this number, you can have 6 in the first dice, 6 numbers on the second dice, 6 on the third, and 6 on the fourth. So 6 times 6 times 6 times 6 is 1,296. Same thing over here. 216 is 6 times 6 times 6 for 3. And then this one is 6 times 6, which is 36. So that one's more manageable. So once you find all of your possible rolls and your means and your frequencies, you would have these numbers. And like I said, I think I just looked it up instead of listing it all. Using the calculator, still this would be L1, this would be L2, same thing. Your mean is still 3.5, it's never going to change. Standard deviation is 0.85, so it changes. And then here's your graph for n equals 4. So what you should notice, and we'll get into the sampling distribution here, what you should notice is we started off with 1 dice for here, and it's just a straight across uniform distribution. If I can talk, maybe. That one's uniform. For n equals 2, it is a normal distribution. I stink when I try to do this, but it looks something like that. For n equals 3, it is even more normal than n equals 2. And I didn't put n equals 4 on there, so let me just do it over here. For n equals 4, let's get that out of the way maybe. For n equals 4, I wish I could draw better, but it's even more normal. And if you went up to n equals 5, n equals 6, if you keep going up and up and up on n's, you would keep getting a more and more normal curve, getting closer and closer to what looks like the standard normal curve. It would just keep getting more. These numbers, you would start getting closer together and it would smooth out even more. So obviously bar graphs got jagged edges and stuff, but the more more dice you use, the bigger your n is. This is just going to smooth out, which is the whole idea behind your sampling distribution and central limit theorem. So now if you go back to the first page, we'll actually do the definitions. I think it makes a little more sense if you look at the example with the dice first, just because it helps you kind of see that we started with uniform distribution, but as we increased our n, it gets more and more normal. So x can be a random variable with a normal distribution. It has a mean mu and a standard deviation sigma. The x bar is the sample mean corresponding to random samples of size n taken from the distribution. So this words make it make no sense, but when you actually see a problem done, it's pretty straightforward. What's true is your x bar distribution is also normal. The mean of the x bar distribution is the same as mu, which we saw on the dice. Our mean was always 3.5, didn't matter what it was. The only thing that changed on the dice was our standard deviation. So your standard deviation is actually standard deviation divided by the square root of n, which I can show you here. Our standard deviation of our original distribution was 1.71. And according to that theorem, and I know we're not starting with the normal, I'll talk about that in a second, but according to that theorem, this is supposed to equal sigma divided by the square root of n. So our sigma originally was 1.71 divided by n on this one is 2. So if you go to your calculator and do 1.71 divided by the square root of 2, you get 1.209, so 1.21. The last decimal may be off, just because you might get a little bit of a rounding error if you do it on the calculator versus using the formula, but as long as it's close, within a decimal point, that's okay. This one, same thing. Sigma was 0.99, we know. If you check the formula using your original standard deviation from our original distribution, it's 1.71 divided by the square root of 3 this time. So 1.71 divided by the square root of 3 gives us square root of 3 gives us 0.987, so 0.99. So those also match. For n equals 4, same thing. 0.85 is what the calculator said, so check it using the formula. We're going to do our original sigma, which is 1.71 divided by the square root of 4. So we would have 1.71 divided by the square root of 4 is 2, 0.85. So here's one where you might get a little bit of a rounding error, 0.855, so you might say 0.86. The calculator rounded to 0.85 when you did it on the calculator. So if it's something like that one decimal's off, it's just a rounding error is all it is. So you can see that formula, it's not actual proof since you can't use an example as proof, but it's good enough for statistics for now. So we can use this theorem to draw conclusions about means of samples taken from normal distributions. If the original distribution is normal, then the sampling distribution will be normal. But you notice here, we started with a uniform distribution and actually turned into normal. So that's the other part of this, the other theorem. So your new notation is mu sub x bar is equal to mu, and sigma sub x bar is equal to sigma divided by the square root of 10. So let me find that. Let's see. I changed this for the dice. This was our original distribution. This is our new notation. So I just added that over here. So if you wanted, you could add that on your notes. What this is really called is mu sub x bar, which is the same as mu, and this is actually called sigma sub x bar. And same thing here. This is mu x bar. This is sigma x bar. The standard deviation of your sampling distribution, the sigma divided by the square root of n, is called the standard error of the mean. That's just the definition. And what some people get confused is standard error versus standard deviation. Standard error is an estimate of how close to the population mean your sample mean is likely to be. If you have a big population of say 100 things and you pull 50 of them out of it, then those 50, the question is how close is your mean of 50 to your mean of 100 in your population. Standard deviation is the degree to which individuals within the sample differ from the sample mean. So standard deviation actually tells you your mean's always in the middle, and standard deviation tells you if it's above the mean, below the mean, and how, like if you do a standard normal, exactly how far is it from the mean. Your standard error should decrease with larger sample sizes. So like I said, if you have a population of 100 and you pull out 50, if you pull out instead, say 90, then the mean of those 90 should be really, really close to those mean of 100 because you've almost pulled out the whole population. And then the standard deviation is unaffected by your sample size. So to calculate z-scores, and like I said, this is a lot of vocabulary and notation, but you'll see it's actually done, you do these problems the same as we did last week. The only thing that changes is you're talking about x bar and mu sub x bar, but x bar is just going to be treated like x. Mu sub x bar is the same as mu, so the numerator is still basically x minus mu. You just say x bar now. And the only thing that changes is your standard deviation. So your sigma sub x bar is you use this formula, sigma divided by the square root of n. So it's a similar formula, it's just not, it's just tweaked, this denominator is tweaked slightly. So to do this first problem here, the time it takes to drive between cities A and B is normally distributed with a mean of 14 minutes and a standard deviation of 2.2 minutes. So there's our mean, here's our standard deviation. Find the probability that a trip between the cities takes more than 15 minutes. So if you notice here, this says a trip. A trip means one trip. It does not mean 2 trips, 3 trips, 4 trips. A trip is just one trip. So for one trip, you're going to be doing this like we just did last week. Because if you recall from last week, we were talking about normal distributions, and it was always like SAT scores or whatever we were, whatever example it was. It says if one SAT score, or, what do you have to score? So we were only talking about one thing. So a trip is just one, so we do this like we did last week. So mean of 14 goes in the middle. 15 would be to the right of that. And we want more than, so we're going to go this way. So our z, using our formula from last week, is x minus mu divided by sigma. So we do 15 minus mu is 14 divided by sigma is 2.2. That gives us 0.45. So the probability that x is greater than 15 is the same as the probability that z is greater than 0.45. Using our chart, if you remember, for greater than, you always have to remember to take it away from 1 because the chart gives you the area to the left, not to the right, so you have to subtract it from 1. I get my positive piece out here. So go to 0.45, it's up here, over to 0.05, you get 0.6736. So if you do 1 minus 0.6736, you get 0.3264. So that's just what we were doing last week. So what changes for this week is this problem says find the probability that mean time of 9 trips between the cities is more than 15 minutes. So now we're not talking about just a single trip, we're talking about 9 trips. So when you do these, you need to be able to read, make sure if you're talking about 1 versus if you're talking about more than 1. So we're talking about n is 9. So when you see that you're talking about more than 1 trip, that's your clue that you switch to x bar. instead of just x. So what we're going to do is we'll say our mu sub x bar is the same as mu, which it told us was 14 over here. Our sigma sub x bar is sigma divided by the square root of n. And the reason this is your clue to switch to x bar is because they're not going to tell you 9 if you're never going to use 9. If you tried to do it just the same way, you never plug in 9. You just do 15 minus 14 divided by 2.2. So they're not going to give you a number that you don't use. So you have to use that somewhere. So this is where you use it. So we would do 2.2 divided by the square root of 9, which is 0.73. And on these, if you round these numbers, if you type them in on the calculator the way they are, that's fine. If you just have to remember to put parentheses where you need parentheses. If you round them here and then use the rounded value, sometimes your last decimal will be off, but as long as you're within a decimal or two, I give you credit. So if we were to draw this, it would look the same because here's 14, here's 15. That would be the same, but what changes is that instead of talking about just one trip, we're talking about 9 trips. So our z now is equal to, you still do 15 minus 14, so the numerator is the same as before. The difference is the denominator. Instead of dividing by 2.2, you divide by 0.73, which gives us 1.37. So the probability that x bar, because it says the mean of 9, so x bar means x bar for a sample. You could say mean of 20, mean of 30, whatever. So mean of this sample. So probability that x bar is greater than 15 is the same as z being greater than 1.37. Again, you have to remember to take it away from 1. So 1.37, we go to 1.3 over to 0.07, 0.9147. And you get 0.0853. So that's a problem from last week, which is here, versus a problem from this week. So like I said, it's almost the same. The only thing that changes is you have to do this new standard deviation. Here, you do the sigma divided by the square root of n. So it's actually called the standard error, but most people just think of it that way. But you do this new part, and then the rest of it's the same. So just pay attention. If you're talking about more than one, that's your clue to do x bar. So if you go on to the next page, it says what happens if the original distribution is not normal, which it wasn't when we were talking about the dice, when I went ahead and went over the dice, because the original distribution was actually uniform. So if the original distribution is not normal, you're going to use the central limit theorem, which basically says if you have any distribution with your mean and standard deviation, the sample mean based on random samples of size n will have a distribution that approaches the normal distribution as n increases without limit. How large should the sample size be? Usually 30 or more. You saw on the dice, it was actually normal. Where my pictures go? Usually you need an n of 30 or more. Well, I lost my graphs here. But you saw with this dice, it actually went, once you went from n equals 1 to n equals 2, it was already normal. 2 made it normal. And then like I was saying, the higher you go with n, the more normal it's going to get, the smoother, because the smaller the bars are going to be and the smoother it's going to be. So you'll end up with bars that are super close together, you know, like this. And they're really, you can't hardly distinguish that they're even a bar, something like that. So the higher you go, the more normal it'll get. So this talks about sampling distribution and central limit theorem with the dice, because we started with the uniform, and then like I just said, it became normal after only doing 2 dice. So we already, and the formulas are the same, which we've already shown that the sigma divided by the square root of n works. So for a couple more applications, And well, let me do these helpful hints and then I'll be done with the PowerPoint and then I'll do the applications. So don't confuse your z-scores and areas. Z-scores are your distances along the horizontal axis. Areas are regions under the normal curve. Our table, the book that I pull problems out of is A2, but our table that I posted lists z-scores in the left and across the top. The areas are in the body. Make sure you choose whether it's right or left, or it could be in between. A z-score must be negative if it's located in the left half of the normal distribution, so if it's below your mean. And areas or probabilities are always going to be positive or zero. So if you ever come up with a probability that's negative, that's not right. Z-scores can be negative, but your probabilities cannot. And then I could have added one here. When you see the probability that the mean of a number greater than 1 trip is such and such, that's your clue to do X bar instead of just doing our normal X that we did last week. I guess I should say, because I think I fixed one thing. Okay, so to do a few examples. Records indicate that the package shipped by a certain trucking company have a mean weight of 510, so there's our mean, and a standard deviation of 90, so here's our standard deviation. It says 100 packages are being shipped today, so 100 is our sample size, there is the N. Find the probability that their mean weight, so 2 clues, there's actually 2 clues for X bar. It'll say find the probability that their mean or average, so that it means X bar, and then it'll also give you an N, will be more than 530 pounds. So for more than 530, our mean is in the middle here at 510. So 530 is to the right, and we're doing more than, so we're going to shade that way. So our new Z formula is X bar minus mu sub X bar divided by sigma sub X bar, which is the same as sigma X bar minus mu divided by sigma square root of N. So for this one, Z, if we're doing more than 530, we'll do 530 minus, means the same, so numerator is the same, the difference is the denominator. So you do 90 divided by the square root of 100. Now you can type it in on the calculator this way. If you do, make sure you put parentheses around all this, and the calculator adds 1 for the square root. So make sure you get make sure really it's this big, the numerator in parentheses and this one in parentheses is the big one. So 530 minus 510 is 20. 90 divided by square root of 100 is 10, so 90 divided by 10 is 9. If you do 20 divided by 9 and round, remember Z, you still round to 2 decimals, you get 2.22. So the probability that the mean weight, which would be X bar, is more than 530, so greater than 530, is the same as the probability of Z being greater than 2.22. Again, for greater than, we have to subtract it from 1. Go to 2.22 here, 0.9868. And we get 0.0132. For part B, what is the probability that their mean weight will be less than 500 pounds? So if you're going to do less than 500 pounds, if you were to draw it, means 510 here, 500 will be to the left, and we're going less than, so we're going to shade to the left. So again, Z is less than 500, so we start with that. So 500 minus, our mean is still 510, divided by standard deviations 90 divided by the square root of N. So this will give us negative 10 divided by 9, which is negative 1.11. So the probability that the mean, X bar, is less than 500 is equal to the probability that Z is less than negative 1.11. For that one, you can just use the chart because it's less than. So go to negative 1.1 over to 0.01, you get 0.1335. Between 495 and 515, probability that the mean is between that. We have 510. So 515 is a little bit to the right. 495. And if you don't draw pictures, if you're comfortable doing these without pictures, that's fine. A lot of people find the pictures helpful, so I usually just sketch one just real quick. So we're doing between these two, so 495 minus our mean is still 510, divided by, same thing, standard deviation divided by the square root of n, which is 100. So that one gives us negative 15 divided by 9, which is negative 1.67. For our second z, we have 515 minus 510 divided by, same thing. So that gives us 5 divided by 9, which is 0.56. So the probability that the mean is between these two numbers is the same as the probability of z being between negative 1.67 and 0.56. And if you recall, when you do between two values, you take the higher value, get that area that gives you all of this to the left, and then we subtract off the lower value because it takes away that little piece. So for 0.56, here's 0.5 over to 0.06, 0.7123 minus, for negative 1.67, we go, here's negative 1.6 over to 0.07, 0.0475. So you get 0.6648. So that's a whole A, B, and C for doing our mean distribution. Like I said, your two clues for X bar is it'll say what's the probability that they're mean or average, and then it'll also give you that N. So two more here. Should just move all these. Okay, we have, according to the Energy Information Administration, the mean household in 97, I need to update some of these, but the numbers are okay, it's just an example, was 2.6, so there's our mean with a standard deviation of 1.5. There's your sigma. And it's helpful if you label as you read, because then you'll be able to find stuff. What is the probability that a random sample of 100, there's N, results in a mean, so again, N and mean, that's your clue to do X bar, household size of 2.4 people or less. So if we're doing 2.4 people or less, um, 2.6 is the mean, so 2.4 would be to the left, and this is less, so there's your picture. So our Z is X bar, we're talking about 2.4 people, minus our mean is the same, 2.6, divided by our standard deviation, 1.5, divided by the square root of N, which is 100. And I should also note that these don't tell you, I don't think the last one told you, let's see. Yeah, these don't say if they're normal distributed or not, which is what I was talking about. You know, our dice was the uniform distribution. So it doesn't matter what distribution you start with. You can use that central limit theorem and do them the same. Generally, N needs to be greater than 30. The dice happen to work out with an N less than 30. But so for these, N is 100, so we're okay. I'm not going to give you a problem you can't do, so you'll just do all of these the same. So n is 100 here too, so as long as n is greater than 30, usually the central limit theorem applies, and generally if I give you a problem, it'll work anyways. So just as a little side note there. So this is negative 0.2 divided by 0.15. Basically what the central limit theorem does is just allows you to do the same type problem to convert to a standard normal to get your z-score and be able to find your probabilities using any distribution. Doesn't matter what you start with. So that's all it's there for. So the probability that a mean household size is 2.4 people or less. So if you put a less than or equal to, it's fine. I think I mentioned last week that the equal to part doesn't matter because the equal to is just a straight bar here. So generally you'll see these just less than. You'll never write a less than or equal to. If you do, it's not wrong. It's still the same answer. So the probability that x bar is less than 2.4 is the same as probability of z being less than negative 1.33. And for less than, we can just use the chart. So negative 1.33, 0.0918 is your answer. And for our last one here, the National Highway Traffic Safety Administration, mean age of a driver involved in a fatal crash in 99 was 39.4, so there's our mean. Standard deviation was 17.4. What's the probability that a random sample of 50, so there's our n, would result in a driver's mean age, so again there's your clue to be x bar, n and x and mean, is greater than 35. So mean is 39.4, 35 is over here, and this time we want greater than, so we're going to shade to the right. So there's your picture. So z is same numerator, 35 is what we're looking at as our data value, or x bar, minus mu sub x bar, which is the same as mu, 39.4, divided by sigma x bar, so we do sigma 17.4 divided by the square root of n, so 50. So again, for this one, it doesn't tell you if it's normally distributed, so your n needs to be more than 30, which it is. But like I said, I won't give you a problem you can't do. So this gives us negative 4.4 divided by 2.46 if you want to do the decimals. Which is negative 1.79. I think for this one it actually works out either way. I think it gives you the same. But just so you can see one real quick on the parentheses, what I was talking about. If you type it in all at once, you need to put your numerator in parentheses, so 35 minus 39.4. Close that parenthesis and then divide by, and that has to have a parenthesis 17.4 divided by the square root of 50. Now if you leave off the last two, it doesn't matter. As long as you have the numerator in parentheses in this first one, it knows that this last thing's a group. So you can hit that and it'll do it. If you're a little type A and don't like to have the open parentheses, you can put 2 there. It'll give you the same answer. But the big thing is make sure your numerator's in parentheses, and then you make sure you add this third one here to group the bottom. So that's negative 1.79. So this is where if you type it in this way, not on this problem, it rounds to the same, but if you type it in this way versus using, if you do piece by piece and do the decimals, your last decimal may be different, like it might have been negative 1.78 instead, but as long as you're only one decimal off, I'll still give you credit. So just keep that in mind. Sometimes you might get a little bit of a rounding error. The safer thing to do is to always just type this in and not use these rounded, well, this one's not rounded, but this one would be rounded. But as long as you're within a decimal, it's fine. So the probability that our mean is greater than 35, so x bar is greater than 35, is the same as our z being greater than negative 1.79. And again, for greater than, you have to subtract it from 1. So 1 minus the value for negative 1.79, go all the way over, 0.0367. So 1 minus 0.0367 is 0.9633 as your answer. So this section for this week is similar to last week. You're just tweaking the denominator, basically. And I think on your homework, just to give you a couple hints here, let's see. This is done like the dice, just so you can have a clue on where to start. It says the age of your 4 U.S. presidents that were assassinated in office. Here their ages are. You're going to select 2 of them randomly with replacement. List 16 possible samples. So just like with the dice where we did 1, 1, 1, 2, 2, 1, dotted off, so on and so forth. So you'll have 56 and 49, 56, well, actually you could start 56, 56, because it's with replacement, so you can select the same one twice. So 56, 56, 56, 49, 56, 58, 56, 46, and then move on over to here, 49, 49, 49, 56, 49, 58, etc. So there's 16 of them. And then you have to find the mean of the 2 numbers. So once you do that, you'll find the mean. And then you can put them in order if you want. It doesn't matter. Some people do, some people don't. So mean, find the mean of the 2 numbers you have listed here and count their frequency. And then you should have all these used filled in. There's no extra. And then calculate your mean and standard deviation. For the population mean and the population standard deviation, this is your population, 56, 49, 58, and 46. That's your population for that one. The mean of your sample means and the standard error is referring to this chart here, where you do L1, L2, and then go to stat calc L1, comma L2. And then it asks you, is this the same as mu, and does it equal this? If it doesn't, then you probably want to look again. And then for the second page here, it says assume the SAT scores are normally distributed with the mean of this and a standard deviation of this. For part A on all these, it says if you select one ACT score, SAT score, that's how we were doing it last week, because you're only looking at one. So you're just going to use the normal Z formula that we used last week, the x minus mu divided by sigma. And because these are normally distributed anyways, for the part B's, it doesn't matter what the n is. You don't need the central limit theorem. If it starts out normal, then all your sample distributions will be normal. So n can be less than 30. So that's what I was saying. I'm not going to give you a problem that you can't do. So generally, if it doesn't tell you what the distribution is to start, n will be more than 30. This one, it tells you it's normal to start with, so it doesn't matter what n is for your part B's, because for your part B's, it gives you an n. Find the probability that they have a mean. So the part B's are going to be your x bars, like I was doing this week. So that should be enough of a hint, I think, to get you started here. If you have any questions, please just let me know.